like watching PowerPoint slideshows, others maybe do not. Some maybe like writing notes down. We're going to try to have a balance of the two here, and I hope this works overall. If you have any comments, questions, or criticisms of this approach, please let me know, and we'll make changes as we go along. I think it's best to try to write things out, and this is my attempt to try to like be in the classroom writing things on the whiteboard, and so that hopefully it's somewhat helpful, but we'll see as we go along. So there, I'll disappear here, and now let's look at, this is an outline of notes that I had posted on Beachboard. If you haven't looked at it already, I encourage you to please either download it or we'll write this as we go along. So the goal for each of our classes is we'll have that short video, which we'll use some PowerPoint, and then during our class time together, to try to do it as if we were writing things on the whiteboard. And hopefully this will make the time in class be really effective as you'll be writing things down and writing out your notes that you'll use for studying. So now let's go forward actually into new material, because as mentioned, this summer class moves relatively quickly. And let's get into this discussion of carbonyl group chemistry and organometallic compounds. And this carbonyl group will actually be one of the major components that we're going to be discussing all semester. And so to help with this introduction, and if this seems like you, that's great, because it probably is, but I just want to make sure that we're all kind of starting off together. So remember, as we discussed, it seems like an hour ago, but it was about 10, 15 minutes ago, maybe 20 minutes. We saw that if we have this alkyl bromide here, we could carry out a substitution reaction. We could replace this bromide. I think we did chloride for bromide, but it's the opposite here. So bromide, we could replace this with a chloride, and we had an SN2 reaction. Let's just put that in there so we remember. So this was our substitution reaction. Other types of reactions, this is one that we didn't discuss yet, but we could take on the right side here, we have this alkene, and we can add something to it. In this case, we added a bromo, and there's a hydrogen that's not shown here. So we added HBr, actually across that. Double bond, clever name, is an addition reaction for adding HBr. And those are some of the main types of reactions that we've seen up to this date. So now what we're going to really focus on for the next few weeks are reactions with the carbonyl group. So let's just first, as mentioned, hopefully review. Think about what is the carbonyl group, what's so important about it? Well, the most generic form is that the carbonyl group is this carbon double bonded oxygen. And why do we care about this group so much? It's because it's reactivity. It's going to be reactive in so many different types of reactions that we can see. And right at the outset, I'll just put it here next to it. You can think about this carbonyl group here. We have two lone pairs of electrons here. And we have an oxygen that's much more electronegative than the carbon. So we could represent this as a dipole in this direction, which means that this carbon here is going to be electrophilic. And that's going to be one of the we'll call it philic, key features of this. And to help even exemplify that more, we could actually draw a resonance structure here, where we can take a lot of red, move these electrons up onto this oxygen, and draw a resonance structure. Negative formal charge, positive formal charge. So this helps even, I'm going to erase that. We'll just put the arrow in there. It's not quite proper, but hopefully gets the point across. So that helps it demonstrate even more that carbon is electrophilic. And so what we're going to see is we're going to react this with a wide variety of different nucleophiles. And while we're at it, to help even show this a little bit more, let's think about the structure of this generic carbonyl group here. We'll turn it on its side. So we have a carbon, an oxygen. Let's have an R group coming off here. Another R group going into the back. And then notice we have the double bond that's represented by the left structure of our resonance structure. So we have this pi system here. I'm sure you can draw it much better than I can. It looks like this. And so the key thing here is that this carbon, it's sp2 hybridized. Trigonal planar, right, is the geometry here. So what we're going to end up seeing is that we'll be able to have nucleophiles attacking this carbonyl group, either from the top face or the bottom face of this carbonyl group. And that's going to be important later on as we start thinking about stereochemistry of our reactions. So here I just wanted to set up that the carbonyl group C double bond O is going to show up a lot in our discussion. It's going to represent an electrophilic center that we're going to have here. We can show that by this resonance structure. Now this, of course, the one on the left is the major contributor, using the language from 220A, but this is going to be a way of representing that this carbon is positively charged, which means it's electrophilic. So a variety of nucleophiles could attack this sp2 hybridized carbon of the carbonyl group. Now, as part of many functional groups, I don't want us to memorize these, but just know them by use, which means memorize in a way, but we're going to see them quite a bit. And rather than just seeing 20 different functional groups, we can see a couple of trends of these groups. And I'm sure you've already discussed these. So let's have a carbonyl group with a hydrogen on one side and an R group, which is some carbon-containing group on the other side. And then let's look at one more here that has carbonyl group sandwiched between two R groups. It's not a hydrogen. So this side is our aldehyde. And this is an example of a ketone. So I'm going to use that language. Now, let's consider a few other functional groups. Still, the carbonyl group is the common feature. Let's use a chloride on one side. And we could have one on both sides, but I'm just showing another one. Let's have our group with an oxygen and some other alkyl chain. How about, rather than a R group, let's have a OH. And then last for right now, let's have a nitrogen. So just put a hydrogen there and some other R group there. So these are all going to be functional groups that we'll see in the next couple of weeks. And to get the language out there, this is an acyl, or sometimes known as an acid chloride. Spell chloride properly. This is an ester, or this acid, the carboxylic acid. And last, this is an amide, or amide, as some people say. There are different varieties of these different functional groups, but they're going to come up again. And so when we use the language about, oh, what do we have as a reagent or a starting material? Oh, it's a carboxylic acid. We know what that is. One other thing to think about when dealing with these functional groups is that, and I'll highlight the one on the left, this whole group here, the carbonyl group and the hydrogen, is the aldehyde. Thinking about the two R groups, this is the ketone. This whole carbonyl group with the chloral group there is the acyl chloride. So in other words, we cannot separate the two. And I'll go over to the carboxylic acid. This is where it happens most frequently. This is not a ketone and an alcohol. It's not that. This whole group is the carboxylic acid. And the reason why we have to treat this as an entire group is we could think about resonance, actually. We have two lone pairs of electrons on this oxygen. We could draw a resonance structure where these dump these electrons back into here and up under this oxygen. And then we could even put the hydrogen up here. So we see that these two groups can be similar. So that'll be important now, because one of the things we'll be doing in the next couple of weeks is spreading out to seeing all sorts of different functional groups. In the first semester, it's an alkyl chloride and maybe an alkene and so on. Now we have all of these functional groups. However, whereas there seems to be a huge number of functional groups, what we can do is also think about the very common trends in the reactivity. And one of the first things to be thinking about here is, and this is how we're going to approach this, it's really the aldehyde and the ketone. This is not really grammatically the best way to say this, but there's no good leaving group. And we'll see this a little bit more. The leaving group, in this case, would be a hydrogen, the negative charge, which is going to be highly unfavorable, or a carbon-containing group with a negative charge, also highly unfavorable. It can happen, and we'll see cases maybe where it does. However, if we compare that to all of these species, we'll say have a potential leaving group. And they're actually, leaving groups come in varying goodness, for lack of a better word. And this order here is not actually arbitrary. And it turns out that the acyl chloride is going to kick out chloride, which we already know is a good leaving group. And that's going to be a better leaving group than oxygen with a negative charge and then nitrogen with a negative charge. So what I'm trying to set up here is something that we'll see probably like towards the end of next week or so, where we're going to see all of these different sorts of groups containing carbonyl groups that have different leaving groups. And that's going to be the different part. However, the similarity is going to be focusing on the carbonyl chemistry that we have here. So to recap this, don't want us to memorize all of these functional groups, but to learn them by using them. And what we'll end up doing is we'll be focusing more first on the aldehydes and ketones because they do not have a good leaving group, and then later into all of these other groups that have a much better leaving group. Okay, so a lot of new information. That's not enough. Let's keep going forward.